Okay, before we get into any new content, I'd like to go over the answers to the class exercises from today. So, as we talked about, if you're trying to design an algorithm that's n cubed, a surefire way to do it is to put a loop within a loop within a loop. Okay, so just to show you, exercise 1, an algorithm that is O n cubed would be the following. So let's say, I have a method, do cubic, I pass it in an array, something like for x in array, for y in array, for z in array, do something that costs at most a. Well, this is going to take, my timing function here is going to be so assuming that the length array is length n, then this takes n steps. But for each of those n steps, it does these n steps. And then for each of those n steps, it does these n steps. So let's be a little more specific. So this really takes a times n steps. This loop does the a times n steps n times. And then this loop does the a times n times. So we see that t of n is equal to a n cubed. Which, pretty straightforward then, you can see that the t of n is big O of n cubed. I already have my constant, it's a. Okay, so that's the first exercise. I want to make sure that was clear. Okay, for the second exercise, we're looking at this function. So now we're not even thinking about an algorithm, we're just looking at a function to make sure we understand big O. So for exercise 2, I said that my function is n squared log base 2 of n plus n cubed. And my claim was that f of n is big O of n cubed. So another way to interpret this is that somehow the n cubed term dominates this term. Now, one fact that I can use to help me with this, is that n is, log base 2, oh no, I'll say it the other way. N is greater than log base 2 of n when n is greater than or equal to 1. So this is true. So just to give you an idea, let me actually plot this, because I think it's much easier to look at a plot. Although we're not going to proof by plot. I'm going to show you in the very next video how we rigorously prove this, but for now, what I'll say is n is equal to np.arange 1. Let's say we'll go up to 128. And then I'll say lg2n is equal to np.log base 2 of n. I'll plot n by itself. And then I'll plot log base 2 of n. So let's have a look. I need to import this first. Okay, so it's pretty clear here that log base 2 of n is completely swamped by n. Maybe I'll actually go even smaller so you can see it. Yeah, so this whole time n is completely beating log base 2 of n. Because for example, log base 2 of 8 is 3 because we need 3 factors of 2 to go into n. So remember what log base 2 of n means. Log base 2 of n is saying how many factors of 2 do I need to put in to get n? So, for example, log base 2 of 8 is equal to 3. Log base 2 of 32 is equal to 5. So 2 to the 5th power is 32. 2 times 2 times 2 times 2 times 2. Okay. So what we can do is, look, if I'm trying to show that f of n is big O of n cubed, what I have to do, let me copy this down here so we can look at it. What I have to do is I need to find a constant c so that this whole thing is less than or equal to c times n cubed. That's what I need to prove. So one thing I can say is since n is greater than log base 2 of n when n is greater than or equal to 1, then I can simply, it's definitely true that if I take this original equation and I replace the log with an n, then this is true. Oops. Okay, so what I did was I replaced the log base 2 of n with an n, and actually this is going to be a strict equality because n is greater than log base 2 of n. So I just made this bigger. Okay. In the process, I also made it easier to analyze because what I can show then is if I simplify this, this is going to turn into n squared times n is n cubed, and then I can simplify that even more to just 2n cubed. So look, I just found my constant. It's 2. Okay, so constant c equals 2. So in other words, n cubed dominates n squared log n. So if I replace the log n by an n, I can fold the n squared log n to n cubed, showing the whole time that this is all greater than this. And that's all I needed to do to establish my bound here. Okay, so let me know if this isn't clear and if you have any more questions. I'm just trying this whole time to establish an inequality. Okay. So I want to find something that's an upper bound for my f. And so I'm allowed to replace something in f by something that's bigger because I'm trying to find an upper bound. So it's totally fine if I make the thing bigger. And in doing so, I make it easier to analyze. Okay. All right, let's go on to the next problem. So let's say we have a function a log base 2 of n squared. So the claim, okay, so here's exercise 3. So the claim is that f of n equals log base 2 of n squared is actually O of log n. I'll say log base 2 of n. I mean, that seems a little weird, right? We certainly couldn't do that with polynomials. I couldn't say that n squared is O of n. So how could I say that log of n squared is O of log n? Okay, but logs are a little different from polynomials. So let me actually plot this to give you an idea. So I'll say n is equal to np.a range 1. I'll go from 1 to 100. No, that's growing too slowly. I guess I'll go 1 to 20. Okay, so let me say log 2n is equal to np.log 2n. And I'll say log 2n squared is equal to np.log base 2 of n times n. The 2.plot log n log 2n gives it a plot n log 2n squared. Okay, so this is the first one. We're going to do just the regular log base 2 of n. The second one we're going to do, log base 2 of n squared. Okay, so what you notice actually is you can kind of see they have the same growth rate. It's just that log base 2 of n squared, turns out it's actually double log base 2 of n. So let me show you that. If I actually do a third plot here and I multiply log base 2 of n by 2, then I'm actually going to get the same thing. So this is interesting. Raising something in the inside of a log to a power actually acts as a multiplicative factor on the outside of the log. So actually, this curve went over the other one. Let's see, so what is line style equals dash dash. Okay, so anyway, now I can see that 2 times log base 2 of n is on top of log base 2 of n squared. So you could use this identity of logarithms that says, I wrote it down here, but log base a of x to the b is b times log base a of x. All right, so I'll just repeat that here. So log base a of x to the b is b times log base a of x. Okay. All right, so in this case, we have log base 2 of x squared. So that tells us that f of n is log base 2 of n squared, which we can rewrite as 2 log base 2 of n. Cool. All right. Now, this is just a constant. So it's really no problem now to show that this is O of log base 2 of n. So this is kind of a surprising fact, but it doesn't matter what power we raise n to on the inside of a log. It's going to still be log of n, O of log of n. Okay. I could raise n to the 1/1,000,000th power. The 1,000,000 is just going to come out as a coefficient in front of the log. Okay. So hopefully everybody's seeing that. Okay, last example. I was asking you to come up with an algorithm that would take n squared log n. So I threw that term up here in this example, but the question is, can you come up with some code that takes that long? So, you know, I would like to challenge you to think of this on your own. So if you didn't get to this, pause this and make sure you can do this on your own. But in the interest of time, I'll go through the answer just so you can see it. But do make sure you take some time to think about this on your own. All right, so exercise 4. Find an algorithm that is O n squared log n. One of the things that we said is sorting algorithms, like merge sort, take what we can say the timing function is t of n is equal to a n log base 2 of n. So we'll talk more about merge sort in a few weeks. You've probably seen it before. I showed it in both 173 and 174. But anyway, you can say that's the timing function for merge sort. So one way to make this happen is to just sort an array n times in a loop, or something like that. So a very simple algorithm that would do this. We take in an array and we say for I in range n, array equals sorted array. Okay, so in here I'm saying all this takes a n log 2 of n. But we do that n times. So then we have this all takes a n times n times log 2 of n, which is a times n squared times log 2 of n. Okay, so that's a simple example of how you could get this. All right. Oh, actually, though, let me go through one more example, which is kind of interesting. It's kind of a combination of the above exercise. Let's say that, okay, so we still pass in an array of length n, but let's say that we construct a new array. And we're just going to push the array onto the end of this n times. Okay, so ARR2 has n squared elements. okay? Because I just added n elements n times. Okay. One common place where this comes up is when you're making a matrix or a table. If it has n rows and n columns, it's going to have n squared elements. So this is very much like the homework that you're doing now. If I wanted to sort those n squared elements, I could say ARR2 is equal to sorted ARR2. And what's interesting is this actually takes O of n squared log n. Because, okay, if I use this formula here, the timing function, that's going to be A times n squared times log base 2 of n squared. So it seems, I would say, well, okay, let me write this down here so we can actually see it more easily. It seems like, so if my timing function looks like this, then shouldn't I have, shouldn't it be O, big O of n squared log of n squared? But again, we can bring this squared outside. So really I can rewrite this as that's 2a n squared log n. All right, so that's how you show. So kind of interesting that even though we're sorting n squared numbers, yes, the term on the front of a n log n, that's going to be n squared when we plug in the n squared. But it's still going to be an n in the log. So this is actually a case that I've dealt with a lot in my work. So this really does come up. So sorting the numbers in a table, that takes n squared log n time. So that's a pretty common algorithm with this time complexity. All right, so those are the answers to the exercises. Now we'll move on to a new concept.